Reionization started when the first light was created by the first stars and/or accretion disks around black holes. It marked the end of the Dark Ages. At that time, extremely strong ultraviolet radiation was produced with enough intensity to drive the electrons out of their orbits around protons. Over time, the density of molecular hydrogen in the IgM was reduced to the point that light could travel across the universe. Spectra from distant quasars show that Lyman alpha forests grow denser with redshift until it leaves no flux behind and becomes a Gunn-Peterson trough. This marks the end of reionization around Z equals 6, when the universe was around 1.1 billion years old.
In this simulation, the dark regions are filled with hydrogen atoms. The light areas have been ionized, and light can travel through it with minimal losses. Over time, the ionized regions around stars cleared entire galaxies, and ionized regions around galaxies cleared entire galaxy clusters. This process ended around 1.1 billion years after the Big Bang, with all of space cleared for light travel. In order to better understand how this reionization actually worked, the James Webb Space Telescope was built with infrared capabilities designed to observe this process that began 13 billion years ago. Here's an image taken by Webb in 2023. There are more than 20,000 galaxies in this field. The hyperluminous quasar J0100 plus 2802 is at the center. It is one of the most luminous quasars known. Its supermassive black hole is 10 billion times more massive than our Sun. Its redshift is 6.327. That gives us the distance the light traveled to reach us at 12.8 billion light years. A deep study of this area was conducted by the Emission Line Galaxies and Intergalactic Gas in the Epoch of Reionization Survey, EIGER for short. The survey used Webb's two near-infrared camera modules, each with a 2.2 by 2.2 arcsecond field of view. Here's their exposure map around the quasar. The study covered 117 galaxies within 650,000 light-years of the quasar. Some are closer to us than the quasar, and some are further away. All these galaxies existed near the end of the era of reionization.
As Lyman alpha emitters, they will all be sending Lyman alpha photons our way. As the photons pass through volumes of molecular hydrogen, we would see Gunn-Peterson troughs. As they pass through space with smaller volumes of molecular hydrogen and smaller volumes of ionized hydrogen, we would see a mix referred to as Lyman alpha forests. As they pass through large volumes of ionized hydrogen, we'd see normal emission lines.
The survey clearly shows that the expected transparent regions do exist around galaxies. The results showed that galaxies near the quasar had fully ionized the gas within a 2 million light-year radius. That's approximately the same distance as the space between the Milky Way and Andromeda. And it showed that the ionization volumes increased over time as the light approached the expected time frame for the fully ionized and transparent universe we have today.
But the timeline doesn't explain what radiation ionized the hydrogen, and it doesn't explain how any Lyman alpha photons, created early in the reionization epoch, could have ever reached Earth.